Great. Thank you. Hi, everyone. I'm Ethan Cecchetti. I'm a third-year grad student at Cornell, and I'm going to be talking about Solidus. This is a protocol for confidential transactions on a distributed ledger using a new building block primitive that we call PVORM. This is joint work with my collaborators at Cornell, Cornell Tech, and the University of Maryland, and we're all members of the Initiative for Cryptocurrencies and Contracts. So let's get started. To start, I want to talk about the way the financial system is structured right now. If Alice wants to send Bob some money, Alice can't just send money directly to Bob. Instead, Alice has to first send money to her bank, which will then aggregate this transaction with several other transactions coming in from other users, send a bunch of money over to Bob's bank, and then Bob's bank will send the appropriate amount of money on to Bob. This all happens within a framework that preserves a large amount of confidentiality. In particular, Alice can't see what's going on with Bob other than this one transaction. Alice doesn't know who else is transacting at her own bank. Alice's bank doesn't know what's going on at Bob's bank. And this is really an advantageous amount of confidentiality. We'd like to maintain this. Unfortunately, this isn't the end of the story. Sitting between Alice and Bob's banks, there's a variety of clearinghouses and regulators and other intermediaries, and these intermediaries introduce fees and delays and uncertainty into the system. And this can make things very expensive, it can make things very slow, and a lot of people, both inside and outside of the financial world, have been asking the question of whether we can remove some of these intermediaries and reduce the fees and uncertainty. And one of the suggestions that's been made for doing this has been replacing things with a blockchain. So why are they asking about blockchains? Well, blockchains provide a very strong abstraction of a public ledger. So people can post transactions onto this ledger, and anyone can go look at the ledger. They can see a transaction on the ledger. They can read who's sending money where, and the whole thing is persistent. It just gets added to and can't be changed later. So if Alice wants to send Bob some money, Alice will just post a transaction onto the blockchain. That transaction says how much money she's sending and who the recipient is. So by the very nature of that transaction being posted, Bob will have received his money. This has a lot of really nice benefits to it. As it pertains to the financial system, it has a very high level of integrity. This ledger is persistent and append-only, which means that Alice can add transactions to the blockchain, but she can't go back and change things later. She can't claim that she sent Bob money when she didn't, and she can't claim that she didn't send money to Bob when in fact she actually did. And this transparency allows for a very high level of auditability. It's very easy for someone, whether it be a government regulator or some third-party auditor, to come in and look at the set of transactions and be able to tell whether or not everything was above board, make sure Alice wasn't laundering money or something like that. But there are also a couple of very important drawbacks as it pertains to the financial system. First of all, this doesn't match with the structure that I had up on the previous slide. This is actually a peer-to-peer system. And in order for us to use something within the financial world, to have it applied in the financial world and remove some of those inefficiencies, we really need it to line up with the current financial system. We're not going to completely restructure the entire financial system. We have to fit it into what's already there. And secondly, the transparency here can be a real drawback. As I mentioned before, the financial system as it currently exists provides a lot of very beneficial confidentiality. And the blockchain in this model removes most of that confidentiality. Anyone can come in and see all of Alice's transactions. Alice knows exactly where Bob is getting his money from and how much money Bob is getting, and some third-party Charlie can come in and see all of this. In Solidus, we aim to keep some of these main benefits, but remove the drawbacks. So we want a bank-intermediated system. We want something where Alice is talking to her bank and the banks communicate with each other and Bob is talking to his bank. We also want all of the data to be posted to the public ledger. This maintains the auditability requirement that was so beneficial about the blockchain, that was really appealing about it, but we also need to maintain the confidentiality that the current financial system has in place. And we need to make sure that Alice can't go look at all of Bob's transactions. It would also be nice if we could be agnostic to the ledger implementation here. We'd like to be able to run this on top of a decentralized blockchain like the Bitcoin ledger, or in a more centralized system where all of the participants know each other. We could use one of a variety of classic distributed consensus algorithms, or even something else, as long as everyone involved agrees on the trust model of this ledger. There have been a few attempts at solving some of these problems. One of them is what we call bank-intermediated blockchains. This is where we essentially remove the intermediaries between the banks and just replace them with a basic blockchain. There are a variety of different platforms that essentially operate on this model that are already in use. JP Morgan Chase has created an open source platform called PVORM that's being used. Digital Asset has one. The R3 consortium of financial institutions is making one. There's Ripple and Stel. The list just keeps going on. I can't fit it onto this slide. Unfortunately, since they're using the basic core idea of this public ledger, none of the information that gets posted to the ledger is hidden. Everyone can see all of it. And that means that banks are leaving information off of the blockchain in order to preserve their confidentiality. So instead of putting all of the transaction information onto the blockchain, they're just putting hashes of transactions on. And this removes a lot of the auditability benefit that we wanted from the blockchain in the first place. If somebody wants to come in and make sure that all of the transactions are appropriate, they still have to go to each of the individual banks and request all of the respective information, and actually trust that those banks are providing them all of the information and that they're not holding something back. Another direction that people have taken is that of confidential cryptocurrencies. These are coins like Zcash that are designed explicitly for confidentiality, and they obscure all of the transaction information. The sender and receiver and transaction values of all of the transactions are hidden, and transactions can't be linked to each other. These are excellent for strong confidentiality. They provide all of the confidentiality we're looking for, but unfortunately, they're still peer-to-peer systems, and so they don't fit in with the existing financial world. Additionally, the implementations of many of these still leave some amount of information off of the blockchain in order to preserve confidentiality and make auditability more difficult. So with Solidus, we want something that doesn't have these problems. So we start with the financial system structure. We have Alice talking to her bank and Bob talking to his bank, and each of the banks has a bunch of accounts. And we'll put all of the accounts and transaction values directly onto the ledger as a starting place to make sure that we maintain the level of auditability that we're looking for. In order to maintain the confidentiality, we then have to encrypt everything. So we encrypt the account identifiers, we encrypt the balances, we encrypt the transaction IDs. This provides good confidentiality, but at first it looks like it makes it a bit difficult to actually execute transactions. We need a way to execute the transactions without just publicly decrypting all of the information and revealing how much money's moving and where it's going. So I'll start with how we hide the transaction values. To do this, we use an idea from Gregory Maxwell's confidential transactions, where we start by employing a homomorphic encryption scheme. In our particular case, we use Elgamal, and that allows us to directly combine, using the Elgamal homomorphism, we can combine the transaction value, which is encrypted, with the encrypted account balances, and we can easily check to make sure that one account was deducted by the same amount that was given to the other account. We can also prove relatively simply that the transaction value is within a legal range. And in this particular case, maybe we want the value to be at least 0, so Alice isn't stealing money out of Bob's account. And we also need to make sure that after the transaction is completed, Alice's account balance isn't negative, so Alice actually had the money that she sent to Bob. This provides excellent confidentiality on the transaction values, but it still leaves a problem, which is that we might be able to link different transactions together. In particular, each transaction, when we perform this update, updates the account balance of one account at each of the respective banks. So if Alice's bank has Alice's account and a few other accounts, we can encrypt all of the account IDs and balances, and then no one can see what belongs to whom or how much money they have, and Alice could say send $5 to Bob, and we update that. We haven't really leaked anything yet, but if Alice then wants to send another $2 or another $3 to somebody else, we can now see that the same account balance was updated multiple times. We don't know that that account belongs to Alice, but we know that it was the same account that performed both transactions. And this essentially is giving all of the accounts pseudonyms, which is the same model that a system like Bitcoin uses, and that was shown by Mickeljohn et al. A few years ago to be fairly insufficient. If you amass enough transaction information, you can just use that linking information to de-anonymize almost everyone within the system. So we really need a way to obscure the access patterns of the accounts. We need to make sure that if Alice's account is updated twice, we can't tell that it was the same account that was updated twice. And to obscure access patterns, we draw on literature from a different area, namely that of Oblivious RAM. I don't know how many people in here are that familiar with Oblivious RAM, since there's actually an ORAM session going on right now in the other room. But we use Oblivious RAM for this as a basic starting point. But Oblivious RAM is designed for a slightly different model. The idea behind Oblivious RAM is that a client with a small amount of memory is trying to outsource memory to a remote server that it doesn't trust for confidentiality. And the client wants to be able to access that memory without leaking any information about it to the server. So not only does the server not know the data that's being stored, it doesn't know the pattern of access that the client's using. There are a variety of different ways of implementing this. The one that is going to be relevant for this work is tree-based ORAM, which was first introduced by Shi et al. In 2011, and then modified to make it more efficient in 2016 by Wang Chan and Shi. And for tree-based ORAM, we organize all of our encrypted data as a binary tree. And each block of data is associated with a unique path along that tree. And when we read the data, we read the entire path along the tree, including that block, but also a bunch of other information. Then, once we've read the data, we associate that block with a new randomly chosen path in the tree, and we put it somewhere along that path. And in this way, we're able to ensure that all of the data accesses look uniformly random from the perspective of the server. Even if you access the same block twice in a row, all the server sees is an access of two uniformly random, independent paths. Unfortunately, ORAM as it currently exists is built for the wrong setting. So in ORAM, the client doesn't need to provide any transparency. The client is just trying to store its data on a remote server, and it wants to get its own data back. No one else needs to know what's going on or know anything about that data. In Solidus, we need full transparency within the system, and so the bank has to prove that it executed all of its operations properly and that it didn't just start changing account balances out of nowhere. In ORAM, we assume that the client has a very small amount of memory. The entire goal of ORAM is to outsource memory to a remote server without leaking the access pattern. Whereas in Solidus, the banks may in fact have a very large amount of local memory, and the goal is quite different. It's to verify the integrity of the system without leaking the access patterns. And lastly, in ORAM, while the client is assumed to have a very small amount of memory, that number is not zero. So it may be able to hide some data locally on its own hard drive, but in Solidus, we can't have that happen. The banks are not allowed to hide data locally. That would destroy the auditability of the system and would likely destroy the integrity as well. Everything has to be posted to the blockchain. And so in order to use an ORAM or an ORAM-like structure, we really have to fundamentally rework how it operates to fit it into this new setting. And our reworking of this is something that we call publicly verifiable oblivious RAM machines, or PVORMs. And they provide three strong security guarantees that are useful in this case. The first one is that they hide the access patterns of the data. This is exactly the guarantee that ORAM provides, and we inherit this guarantee from the ORAM structure that we're going to use to build one. The second thing is that we restrict what updates are allowed. In the case of the financial model, we may say that a given update has to be restricted to a single account at a time, and that account has to have a non-negative balance after the update has completed. And the third thing is that all updates have to include publicly verifiable proofs that they were done properly. They have to include a proof that anyone can verify that says it didn't violate this, whatever restriction was put in place by the second condition. To construct one of these, we start by maintaining the obliviousness by using a circuit ORAM construction. This is the more efficient tree-based ORAM that was introduced by Wang, Chan, and Shi in 2016. And the idea behind a circuit ORAM is that data moves along the paths in the tree using swaps. So we might swap a couple of pairs of data. And because we're using Elgamal encryption, which was particularly useful for confidential transactions as well, we're able to leverage the homomorphism of the crypto system to perform these swaps very efficiently. We also need to verify the integrity of the system. In order to restrict the updates, we use a read, modify, write structure. So if we're going to update a single account, the first thing we do is we read that account using the circuit ORAM's read protocol, and we place that account at the root of the tree. Regardless of where it came from, it always goes to the root. At that point, we can now homomorphically combine the old account balance with the transaction value, the way that we needed to for confidential transactions. And then we can reinsert this new updated account balance into a random spot in the tree using the same protocol that circuit ORAM uses to write values back into the tree. We also prove that all of the swaps we did were done correctly, and we prove that this new account balance is non-negative, and we can do all of this using something called generalized Schnorr proofs, which are simple and efficient mechanisms for proving properties about Elgamal ciphertexts. Now that we have this PVORM construction, we can use it to build Solidus and get the guarantees that we wanted. So we start with this bank intermediated system with a blockchain in the middle, and each bank maintains its own PVORM. And the PVORM of Alice's bank contains Alice's account and whoever else has accounts at the same bank, and Bob's account would be in Bob's bank's PVORM. And in order to perform a transaction, we simply update one account in each of the respective PVORMs. So if Alice sends Bob X dollars, Alice's bank would deduct X dollars from Alice's account in its PVORM, and Bob's bank would add X dollars to Bob's account. This now provides a strong set of confidentiality guarantees. First of all, because we used confidential transactions, the amount of the transaction is only visible to the two banks involved. So Alice and Bob's banks can both see how much money was being sent, but a third party can't. The accounts themselves are only visible to their respective banks. So while Alice's bank knows that Alice was the one that sent money, nobody else, not even Bob's bank, can tell that Alice was the specific account that sent money. It's completely unlinkable from all other transactions coming out of Alice's bank. And similarly, Alice's bank can't tell that Bob was the one receiving money, and neither can anyone else. This is again unlinkable from all other transactions going into Bob's bank. The bank level endpoints are visible, so anyone can see that someone at Alice's bank sent some amount of money to someone at Bob's bank. But even this information can be obscured by adding dummy transactions into the system and making sure that the same number of transactions come into and out of each bank over time. We also provide a strong set of integrity guarantees. First of all, we have a proof that all transactions were authorized by the user whose account balance was reduced. So if Alice is sending money, we don't reveal that Alice was the one sending money, but we can prove that whoever's account was reduced was the person who authorized this transaction. We also can make sure that the balance changes match. This is done simply by using the homomorphic property of the Elgamal ciphertexts to combine them. And we prove that the transaction values are non-negative. And when we combine these, we end up with a strong set of integrity guarantees that form a publicly verifiable proof that anyone in the system can verify. Anyone can come in and audit this. They can look at what's going on and make sure that all transactions were processed properly. So we have this Solidus protocol that has a strong set of confidentiality guarantees and a strong set of integrity guarantees. In order for it to be useful, we need to have some reasonable notion of performance. And I'll start by talking about the performance of the PVORM construct at a basic level. The tree-based ORAM provides very good scaling. It's logarithmic scaling in the number of accounts, so a single bank can have a very large number of accounts and not negatively impact its performance significantly. We also prove the integrity of this using a large number of independent swaps, and so they're highly parallelizable. If we only have one core of a machine running this, it does take a while. But as you can see, the scaling of this is not a whole lot worse than the best possible theoretical scaling of adding more computational resources into either creating or verifying the proofs. Moreover, when we compare this to something like like Bitcoin's transaction throughput in a blockchain-based setting, this is actually a highly practical amount of performance. We also compared this to other potential solutions. In particular, we compared our Elgamal solution using generalized Schnorr proofs to an implementation that used ZK snarks, which is the proof primitive that, that things like Zcash use. And ZK snarks are known for being very, very slow to create. And in fact, we do see that we're about 200 times faster constructing proofs than ZK snarks are. ZK snarks, one of the benefits of ZK snarks is that they're very fast to verify, and we are indeed slower than them, but at a reasonable level of parallelism, we're not that much slower. We're only about one factor of 10 slower. And in the setting that we're targeting, where we have a relatively small number of banks, each creating a very, very large number of transactions, this is really a significantly better performance trade-off. And in fact, we may be in a setting in some cases where we can do some or all of the verification offline, in which case this is even better. When we put this together into the whole Solidus system, we ran a test on Amazon Web Services using Apache Zookeeper as our consensus algorithm. And we ran two different tests. The first one is the brown line at the bottom, where all of the banks were performing verification of every transaction. And in that case, we were actually bottlenecked by CPU cycles because we only had one machine for each bank, and so it eventually ran out of computational power. In theory, we could potentially add many more and get much better performance. We then turned off the online verification to model what would happen if either a bunch of different machines were verifying the transactions or we were just performing offline verification, in which case we ended up being bottlenecked by Zookeeper's bandwidth, which makes some amount of sense because Zookeeper is honestly probably not the best consensus algorithm to use for this particular application. We used it because it was very simple and easy to set up, and it worked out of the box. So as a whole, what we've done is we've introduced PVORM, this publicly verifiable Oblivious RAM machine that provides a new building block for confidential blockchain applications. It moves ORAM into the setting of a blockchain. We've then used PVORM to construct a confidential transactions protocol for a bank intermediated system that aligns with the current existing financial system. And we've additionally proven the security of the Solidus protocol in the universal composability framework, which Manu talked about a little bit in the previous talk. It's a framework that provides very strong cryptographic guarantees. And we essentially have practical performance, especially if we put it in with a little more engineering effort and parallelism, we should be able to get those numbers looking significantly better. Before I finish, I want to quickly say that the name Solidus, we chose this. It was a solid gold Roman coin from the late Roman Empire, first minted in the 14th century. Just sort of a solid gold coin. It had to do with money and seemed solid. And in honor of the Solidus, I figured I'd bring some gold coins with me. These are made of chocolate, so happy Halloween. I have a bag of gold chocolate coins if anybody wants one later. Thank you, and I'm happy to take questions.
Hi, excellent talk. So the question that I had was, you showed the situation where there are two banks and they are performing transactions for their clients with each other.
Yes.
And your motivation is coming from the practical world. So my question was that, let's say I have let's say I have some clearhouse in between. I have multi-hop transactions. If I read correctly, it's not yet possible in this approach, right?
So if you have multiple...
If you have multi-hop transactions, let's say there is a bank A, bank B, and
Yep.
bank C, and money is going from bank A to bank C.
So the assumption there would be that each of the banks would independently be connected to the ledger. They would each have their own PVORM on the ledger. So bank A could send money directly to an account at bank C in that case.
But what if they don't have connection? They always talk with... So you're coming from the... You know what
if they don't have connections, then this doesn't work quite as well. There are a couple of different ways that we could manage that. One of them is we could set up the ledger in such a way that allowed them to get connections more easily. Another option is a smaller bank that isn't connected could make an account at the larger bank, and the larger bank would be connected. And in that case, we would the confidentiality guarantees would look a little bit different because we have this thing coming in from the outside, but we would still be able to have an interaction going on there. It would essentially be a partial switchover from the current system.
Right, that was a nice talk. So my question is that if the Alice's bank, every time Alice sends some transaction, the bank issues a new pseudonym. So in that way, the transaction anonymity could be achieved. So
The bank issues a new what? Pardon?
every time a new transaction happens, a new pseudonym is issued to the to Alice. So how does that solution?
This is essentially our solution for doing that, because issuing Alice a new, we would need a way to unlink the old pseudonym from the new pseudonym.
Yeah.
And either we, and if we just posted the new pseudonym onto the blockchain, we would either not be able to tell that the transaction was performed properly, we wouldn't be able to compare the old balance to the new balance, or we would essentially be able to use process of elimination to figure out which pseudonym changed. If we did it sort of naively. This is essentially our solution to how to grant Alice a new pseudonym without revealing that information.
Okay. Yeah, thanks.
Hi. Could you briefly comment on the perhaps broader applicability of this to non-permissioned blockchains and what would be some of the challenges there? Because you, in your conclusion slide, you said that this as a primitive could be useful.
Yeah.
I mean, in general, you have the same problem of confidential transactions without, say, like Zcash.
This is the PVORM primitive is a little bit hard at first to plug into a non-permissioned setting because it doesn't. Because it essentially assumes there's one entity maintaining a single PVORM, and if you had a bunch of different ones, you would be able to differentiate transactions based on the PVORM. Mm-hmm. You wouldn't be able to differentiate within a PVORM, but you'd be able to differentiate between them. I haven't spent a whole lot of time thinking about that. I think that would actually be a very interesting avenue for future work.
And one other quick question. So the original motivation is to save costs of clearinghouses.
Yep.
So could you comment on the practicality of this? The idea is that making this thing publicly auditable would save costs because there would be good Samaritans auditing it, or I mean, would there just be another proprietary firm that would come along and charge to check
So a
these
lot
proofs?
of the costs and delays coming from clearinghouses, this is not true with regards to cash flow, but things like stocks and other securities, the mechanism by which they're cleared involves long paper trails and a lot of manual work to check ownership of things and takes multiple days. And so the idea would be if we could put, stock information or something like that onto this system, we should be able to remove all of the need for that long paper trail and large delays in manual labor.
Okay. What I understand is that each bank participate in blockchain as a node, right?
Yes.
Oh.
Well, so they can. There are a couple of different models. That's sort of the default model, is that each bank would participate as a node in the blockchain, in a permissioned blockchain.
Yeah.
But we could also have a model where the banks essentially form a permissioned set on top of another blockchain, whether that be decentralized or not. So they all know who each other are, but they may not be the ones maintaining the underlying blockchain.
So if it is compromised, then I wonder how to revoke the...
Yeah, that's an interesting question. The security model here, from the perspective of my bank, my bank doesn't need to trust any other individual bank in the system any more than the consensus algorithm says they do. So if the banks are using a Byzantine fault-tolerant consensus algorithm, then compromising one bank might compromise the users at that bank, but it wouldn't compromise anything else in the system.
Okay.
So I had one quick question. What happens, you guys tested this at 2 to the 15 accounts. What happens if you have, say, 2 to the 30 accounts?
Yeah.
How much bigger did the proofs get?
The proofs get correspondingly bigger. They grow logarithmically with the number of accounts at each bank. We tested it with 2 to the 15 accounts at each bank, essentially because that was how much we could fit in memory on the AWS machines we were running. This on. We did test the performance of an individual PVORM as we scaled the number of accounts up certainly past 2 to the 20. I don't think we made it to 2 to the 30, but 2 to the 30, the proofs would be about twice the size of 2 to the 15.
Okay.
The scaling's logarithmic. Does that? We can take this offline.
Yeah.
Great.
Okay, I was curious how much information would have to be reviewed by an auditor to ensure correctness.
Yeah, that's. I think it depends on what the auditor is trying to guarantee and whether or not the verification is performed online or offline. If the verification is performed online and it's essentially part of the consensus algorithm, then the auditor would be able to ensure that all of the transactions were performed properly and could just go in and look for more, legal audit things, right? Did Alice send money to somebody at the wrong time? If the verification is being performed offline, it could potentially be a significant amount of work to verify all of the transactions. But it depends a lot on what the auditor is trying to do.
Yeah, thanks.
Yeah.